All right. I don't really remember what we had on this, what the loading was, but it doesn't matter. We'll just make up something new. I'll tell you that this is the structure, 35 feet long, some overhangs on the end. I have been told that there is a uniform loading, length of your choice, 2 kips per foot, and the structure is supposed to also be designed for a truck loading with the rear wheels 40 kips and the front wheels 20 kips, and they are 10 feet apart. Now I'm going to generate an influence line for these different conditions, and then we're going to put the loading on the structure such that the structure is critically loaded, and calculate the answer for example, the reaction at B. Here's A, B, C, D, E. If you would like to, you can put a unit load on the structure. I think almost everybody shows like 1 kip. He's trying to listen. Leave him alone. Just kick him if he keeps pestering you like that. Just ignore him. Huh. Yeah, I got to get that roll fixed. You can put a unit load on the structure and solve for the reaction at B. Then you can move it to a new location and solve for the reaction at B. And then move it to a new location and then solve for the reaction at B. And you can plot those points, and that'll be the influence line for the reaction at B. Or you can distort the reaction at B a unit amount, and the structure will turn into its own influence line. So the influence line for the reaction at B, if you distort the reaction at B by the number 1, wonder if I've got a straight edge somewhere. That's good enough. Make one up here. Howdy.
Howdy.
How you doing?
Pretty good.
There's the influence line for the reaction at B. This is the number 1. And that makes sense because if you put the unit load over the reaction at B, it would go right into the reaction, causing a 1 at the reaction at B. This structure has been rolled about the reaction at D, and therefore it has come up to the elevation. 1 is to 20, as Y is to 30, and therefore this would be 1.5. And it goes down to the value. Y is to 5, as 1 is to 20. and therefore y is 1/4. That tells you what influence a unit load would have at any point. So for example, with the 40 kip load, if I'm looking for the max positive reaction at B, not sure where I'm going to write all this stuff. Maybe I got enough, so I just won't do them all. The reaction at B, max, would equal to, first, we'll put the 40 kip load in place of the 1 load at the place where it causes the most influence. And that'll be 40 kips times the number you got for a 1 kip load, 1.5. That's why it's not really a good idea to show you a 1 kip here, because it looks like the influence line caused 1.5 kips here. Then when you plot it, it comes out 1.5 kips. And when you multiply the magnitude of your load times the magnitude of the influence line, it looks like a kip, and nobody knows what a kip is, so it's better really if you put a 1, thereby causing an influence of 1.5 with no units, which you can multiply times 40 kips and get how much reaction at B you get because you put the big wheel there. Next, this wheel's going to go here, 20 kips. It's going to cause 20 times 1, added to your previous number, plus the next thing you do is you put the uniform load spread out as per your choice, and I would put that all the way across until it gets here, and I would say there are no little cars over there. And you would say, well, what stopped the little cars? And I'd say, well, that's where there's a wreck, and therefore they couldn't get on this piece. But they did all bunch up right up to here. And that adds 2 kips per foot worth of loading, multiplied times the area under the influence line between those 2 points. O'Connell, if the influence line is 1.5 tall under this loading and 30 feet long under this loading, and if the area under the influence line is a triangle, what is the area of the under the influence line?
It would be 15 times 1.5, so...
Okay, well, it would be 1.5 for the height. It would be 10, 20, it would be 30 for the base. And because it's a triangle, it's cut in half.
22.5.
Okay, we'll just leave it as numbers so everybody knows where the numbers came from. 1.5 for the height under the influence line over which you have distributed load, multiplied times the base of the influence line over which you have distributed load. You watch your units there. Times 1/2 because it's a triangle. Thank you. No, well, here you go. Just give that to Mr. Condit in the brown shirt there, if you would. Thank you. Thank you very much. Started to get after you for coming in late. All right, and the units are kips per foot times feet. That gives us kips, and that's what the reaction at B is kips. Kips times no units is kips. Kips times no units is kips. You wouldn't have known where to put those loads. I wouldn't have known where to put those loads. I know where not to let the little cars go. You say, well, they'll probably be there. And I say, well, then your structure probably won't fall down. Well, I don't like those words at all. I don't want your structure to fall down, period. I want you to put the loads in the most critical position, and if you have an area in here which is negative, then I don't want you to put little cars there to help the reaction at B. I want to know the worst it's possible that it could ever get. Here is R sub B minimum. By that I mean the negative, the tendency for the beam to lift up off of the reaction. And noticing that this influence line goes negative here, there is some. I don't know how I'm going to do that. Seems like at one time I had a green pen. There we go. I guess I could, gee, I hate to honk it up like that. Let's just do this. Let's just say this is the influence line for the reaction at B. You know how to get the reaction at D just like B. Let me redraw it. Well, let me just show you that here's the influence line. Here's where you put the loads. First off, I'd take the 40 kip load and I'd put it right here where it's the biggest. The influence line height at that point is minus 0.25. Then I'd put the other wheel right here, 20 kips. Because it's 10 feet, oh, that's 10 feet away, isn't it? All right. Where do you suggest I put the little wheel? Off the span. That's correct. Because if you put it here, it will be causing some reduction in that number because this is a negative and that is a positive. So we'll put the 20 kip load over here off of the span where it doesn't help at all. And I would put the uniform load right in here, 2 kips per foot. And the magnitude for R sub B minimum would equal to 40 kips of load placed on the influence line who has a height of minus 0.25 plus a 20 kip load. And it is off the span, so there's nothing for him. And then it would be multiplied times the area under the influence line. And the area under the influence line has got a base times a height cut in half. So it would have a base of 5 feet, a height of minus 0.25, and a 1/2. And that's how badly you better plan on holding that beam down under the worst conditions. And times 2 kip per foot. Thank you. And I let that get in the way there. Thank you. Off plus 2 kips per foot is how high the load is times the area under the influence diagram. Thank you. All right, I'm going to draw an influence line for the shear at C. Here's how I draw the influence line for the shear at C. It's in the middle. I take the beam home with me, and I put it on the curb, and I run my car over it. You can go down or up. The only thing is if you want the right signs to agree with the signs that we're using for positive moments and positive shears, you have to kink it up. There's what the beam looks like after I got through bending it at my house. I deformed the structure with a shear load. I deformed it the magnitude 1.0. And then I brought it back on the job site. And I put that right there and put a pin through it. And right here I see another place to put a pin, but it isn't connected properly to the supports. Therefore, I take this point and I roll it down until it gets to the pin, and I stick the pin in there and I pin it back. That means that this thing right here is going to rotate down 1.0 about this point. If that rotates down 1.0 over a 20-foot length, then this point right here, being only half as far out, will rotate only half as far down. So this deflection is to 10, as your one deflection necessary to get it connected back is to 20. This point here is also going to roll down, because it's the same 10 feet out. It's going to roll down half. And so the influence line is going to look like that. And if you'll pull out your handy pocket moment influence line, shear influence line, reaction influence line generator, you'll see that's exactly what happens. You put a piece of wire on here and it's straight. Take the wire and you put a kink in it. You roll it down. This piece here goes half as far down as the end will. From that you should be able to tell all of the numbers. This number right here is 0.5 positive. This number right here is 0.5 negative. Once you have those, you can get any of the rest of the numbers. 0.5 is to 10 as, pretty badly drawn to scale there, that sticks out there 10, as y is to 10. And so this is 0.5 positive. Y is to 5 as 0.5 is to 10. Y is to 5 as 0.5 is to 10. Slope is the same. And therefore the height y right here is equal to 5/10 of 0.5. That's a half of 0.5. That's 0.25. And it's a negative number. And this is a negative number. Now then the question is, where should you put your loads? To cause V max at point C, use the same notation I used a minute ago, V at C max, meaning the biggest positive moment. House, where would you put the big 40 kip wheel? On the left end would work nicely. Anyone who said put it here would get the same grade, 100%. Whether you put the big wheel here or whether you put it here doesn't matter. Now then, if you put the big wheel here and the little wheel went over here and caused some help, some reduction in the biggest number you're looking for, well then it would make more sense to put the big wheel here and turn the truck around so that the little wheel didn't get down in this negative end. You could just go ahead and it would go on the left side off of the span. But in this case, it doesn't matter. So I'm going to do what you said. I'm going to put the 40 kip wheel where the elevation of the influence line is 0.5. I'm going to put the 20 kip wheel 10 feet away. But it's going to happen to cause nothing anyway. If you put it right, well, there's no such thing. For instance, I'll tell you what, you tell me when to stop the pencil right at C, okay? Nope, that's to the left. So we'll move a little to the right. Oops, too far, that's to the right. Back a little, oops, to the left. Oops. There is no such thing as right at C. There really, I mean, there just isn't. So you're either on one side or the other side. The negative is on the left side. Here, that's a good point, though. It probably would make sense to shade in these influence lines after they're, because you got a bunch of wire running around loose while you're generating it. So that's your influence line. It's a little hard for me to do it here because I already got all my loads shown on here, but basically, here is your influence line, and here is your influence line. All right, Adams, where would you put the uniform load? Those are called lane loadings. In other words, this 2 kip per foot is your choice. You can put it anywhere you want to. Where would you like to put it along this span? And let me redo the numbers because I don't think you can see them anymore. A, B, C, D, E. Where would you put the lane loadings? For positive shear at C. From Charlie to dog is the correct answer. Let me put it down here because it's just too messy up there. You would put it here is correct. That'd be 2 kips per foot. Booth, where else would you put? A to B is correct. Ought to be a little longer because the influence line is also above at that point. And so let me go ahead and put the wheel loads on here too so they're all at least on one picture. That is the way you would load the structure in order to determine the maximum shear at C. And you want to know the maximum shear at C. You have to design this beam to resist shears and moments. Therefore, I'll draw an influence line. I'll tell you that it's your job to solve for the required web thickness in the middle of the beam. We're going to put it together out of 2 or 3 different pieces, and therefore you need to know the maximum positive shear at C, and you tell me what the answer is. Answer would be equal to 40 kips instead of 1 kip times 0.5 plus 20 kips times 0. The only reason I put that in there is just to make sure nobody thinks I just forgot it. Plus 2 kips per foot onto, I use a different looking brace here, this area positive plus this area positive. Or do them separate if you want to, I don't care. The height of this one is 0.5. The base of this one is 10 feet. The area factor is that thing is a 1/2. And then it turns out the other one down here is also 0.5 times 10 times 1/2. So it's times 2 of them. I didn't forget the 2 kips per foot this time. You probably should notice if you miss something, because here you got, if you didn't have the 2 kips per foot, then your final answer is so many feet. And that's not good. But if you got if you missed the 2 kip per foot, you'll know I need a 2 kip per foot. I forgot the load. And that's 2 kips per foot times feet. Feet cancels feet, leaves me with kips. Now with 2 questions, maybe 3, there's obviously something wrong there, but I didn't notice it yet. Yes, sir.
On the 20 kip load, I thought you said that you couldn't be on 2, that you had to be on one side or the other.
Oh, no. I'm sorry. He was asking me what happens if the load goes right at C. And I think what he really was wondering is, to the left, you want me to multiply the answer to the number 40 or whatever the wheel is times 0.5, and minus 0.5. And if it's to the right, you expect me to multiply it times 0.5. I believe his real question was, what if it's right on top of it? It's not right on top of it ever. In other words, and I don't even mind if you say, well, then why can it be right on top of B? Well, okay, I don't mind. Knock it off an angstrom to the left or an angstrom to the right, but it'll still be 0. And somebody else had a question? Yes, sir.
On your beginning structure, you only have one load of 2 kip per foot.
Hang on just a second. You mean this way back original?
Right.
This way back original thing is a spec, and it says design your structure for a lane loading of 2 kips per foot. Then you need to know that any place there's a positive place to put it, you put it in those places and no place else. In other words, you say, I think the chances of having a wreck here and the cars bunched up for 10 feet and then there was another wreck here, you have to account, you have to say that. And of course the numbers are getting kind of goofy here because the whole thing's only 30 feet long. But all I'm trying to do is show you how this works. Now I'm not going to draw it, but I hope you see that if you're looking for the minimum shear, you'd put the big load here, the big wheel where there's a minus 0.5, that's bigger than this one. Go ahead and put the little load here, the 20 kip load, and then cover this negative area with uniform load and cover that negative area with uniform load. So now if you see me make a mistake with the numbers, let me know. Shear at C minimum, meaning negative shear, would equal to a 40 kip load placed at the minus 0.5 location. I don't have signs on them because they're shown below the axis here. You don't usually put minus on there, but it is a minus. Plus a 20 kip load times 0. He'll go here. 40 will go there. Then I'll cover up this area with negative load, and I'll cover up that area with negative load. Plus 2 kips per foot times the areas under the influence line, which are negative. One of them is 0.5 for the height, 10.0 feet. For the base, 1/2 for the area of a triangle. Then I got another little triangle down here. He is, that 0.5 is going to have to say minus. I got to get a minus sign in there somewhere. Minus 0.5. Minus 0, just not aesthetically pleasing. Plus an area which has a height of minus 0.25 times the base, 5 feet times 1/2 because it's a triangle. Putting the big wheels where the biggest numbers are can be found. Then I'm putting the uniform loads over the entire negative parts of the influence line. Yes, sir.
So you're not going to place more than one truck?
Not usually. They usually make you just put one truck. In other words, they design it for one truck amidst all of that other stuff, but you'll be told. In other words, and I can't guarantee that for all specifications. There's AREA, American Railroad, they do things with 20 wheels from their locomotives and everything, and I really don't know all those codes. But if I told you to put 2 trucks on there, my guess is you'd put them both at the same place. In other words, you would say it's a 2-lane road and you put them side by side. But from what I've seen, is one truck and one set of lane loadings. All right. Now then, let's do, I'm just going to give up on all of these names. Well, maybe not. These things were 10 feet long. Let me show the influence line for shear at the 2-foot mark. I would take my original structure home with me. I would put it on the curb at the 2-foot mark, and I would just kink the dickens out of it. And here's where the old pinhole was, and here's where the old pinhole was located when I brought it back out, and I just kind of placed it up there. And I say, okay, well, that's certainly no good. The steel pins aren't in the hole and on the reaction. So what I do is I simply move the entire thing down. I'll draw a wiggly line for the final answer for the influence line. Just that simple. And I tell you what, it always works. Sometimes it's a mess to see what's going on. You got to move it and translate it and rotate it, but it always works. Then, in that case, I would obviously put my big wheel here. I would put the little wheel any way you like, because it wouldn't matter, or I'd put it off the span. I would put the uniform loading right over this area right here, and I would tell the boss it's impossible to get positive shear out of this case. Here's your influence line. And the negative shear will be 40 times 1 and 2 kips per foot times 2 feet. And there's no half because this thing didn't deform into a bunch of triangles. Here is the influence line for the moment at the 2-foot mark. Here's my original structure. I took it home and I kinked it at the 2-foot mark on a 1-to-1 slope. Here's where the old pinhole was located. Here's where the other old pinhole was located. When I brought it back out and made this line up, I noticed that this didn't agree with that, and this didn't agree with that. And so I pushed it up until this hole lined up with that one, at which time it looked kind of like this. And then I rolled it such that this is now straight. Here's your influence line. And it turns out that bends down at a 1-to-1 ratio. And since this is 2 feet, then this 45-degree bend that you put in it, you did too. I saw you bend it. I watched you lay it on a curb and run your Jeep over it. 2 feet. And therefore it tells me where to put the big wheel for the maximum moment at the 2-foot mark. Generally speaking, I probably won't care what the moment at the 2-foot mark is. Well, I will if it's a quiz. I'll ask you for that one. But in the real world, you probably are more interested in what's the moment over the reaction, or what's the moment in the middle, places where things get more exciting. As you see, this wasn't very exciting, but it does show me you know what you're doing. I'd put the big wheel there, and I'd spread load over the entire thing. And I would tell the boss it isn't possible to get any positive moment out of this thing in this region. And if this is a concrete beam, that means the steel is going to go in the top of the section. Here's the influence line for the moment at B. B is right at the support. I take it home. I bend it at a 45-degree angle at B. Here's the pinhole. I bring it back on the job site, and I notice that this pin lines up nicely, and I stick the steel pin in there. This one, unfortunately, has been moved down how far? How far? 20 feet. Because it's 20 feet from here to here, it has moved down 20 feet from there to there. Therefore, it'll be your job to roll the structure up 20 feet. And now then, so far it looks like this. That's a straight line. It rolls up as a straight line. And this is now at a 45-degree angle. And if you want to know how far it is down to there, you could say that 20 is to 20 as this is to that. But if that's a 45-degree angle, you know this is 10 feet over, then this must be 10 feet down. And again, it tells you where to put your wheels and where to put your lane loading. Influence line for the shear. We already did a shear at C. Here we go. Influence line for the shear slightly to the left of point B. Here's what I took home. Here's what I brought back. Here's the old pinhole. There's the old pinhole. That is the influence line for the shear at C. The only problem is it hasn't been properly supported yet. That's your job. Bring this one down how far? 1. Bring this one down 1, and here is your influence line for the shear, slightly to the left of point B. I've shown it a little more than slightly to make sure you see what's going on. The wiggly line is the influence line. This is just a temporary thing that you brought back from your house but hadn't yet put it on the supports. Where would you put the big wheel? Here. Where would you put the little wheel? I'm not sure it wouldn't be fair to go ahead and put it, I don't know what they would do in that case really. They would probably go ahead and put the 20-kip wheel a little to the left, and you say, well, I don't see how that's possible. Dang thing is 10 feet long, and that's 10 feet. Well, I don't know. I think if it was me, I'd probably go ahead and put the 20 on there and just assume the truck was made 2 inches short by accident to get the biggest number that's possible. A theorist, a puritician, probably would say, no fair. If they put the 40 there, the 20 goes on this, and so it doesn't work, doesn't count. I don't know. And the lane loading would go across the top, 2 kips per foot. Influence line now for the shear. Remind me to get rid of this now because here is what I took home. Here's what I did to it when nobody was watching in the dead of night, called vandalism. You'll notice I distorted it slightly to the right of point B. Here is the old pinhole in the piece of steel. There's the old pinhole in the piece of steel. Look at the difference between the influence line for the shear at B versus the influence line to the left versus to the right. Dramatically different. Next thing I do is I go make this pin fit the old reaction. No problem there. I just stick the steel pin in. Next thing I do is I roll this pin down to fit that reaction. It's rolled down 1. And therefore, the structure now looks like this. The question is, how far did that roll down? It rolled down 1. So how far did this roll down? That rolled down further from where it started than this one did, because it is further from the rolling point. 20 feet, 10 feet, 5 feet were our dimensions. Call this total rolling down from there to where it ends up y. Y is to 25 as 1 is to 20, and therefore y is equal to 25 over 20, 1.25. But the first 1 just brought you back to 0. So the height of your influence line on the end is 0.25. Now another way to get that height very easily is simply to say question mark is to 5 as 1 is to 20. And of course, because that's a straight line, you have the same interior angles, you get 0.25 for the height. Now you say, well, wait a minute, if this thing rolled, how come this point didn't go down? I don't know, I hadn't thought about that. Let's check it. The amount that this went down is to how far he is out, as the amount this guy rolled down is to how far out he is. That says that the roll down is to 0 as 1 is to 20, and that gives you no rolling down. And you say, well, I got my little piece of wire right here, and it's moving down. Well, it's because you're moving the wire too much, dummy. You're supposed to move the wire down just a little bit. This is not really 1 mile. It's not 1 foot. It's not 1 inch. It's a 1, a little bitty 1. This is a greatly exaggerated scale. On this end, to keep everybody awake, so you never know when I'm going to call on you. Tell him he's up. Opke North? Raise your hand. That's his name? Well, he must be sitting in your lap then. Opke North? How do you really pronounce that? Opke North? Okay. Opke North, how high is this thing up above the line? Let's see if you can tell me a good answer with all that distraction next to you. 0.5. Well, let me see if I like that. How far this went up is to 10 rolling radius, as how far this went down for a 20 rolling radius. Very good. That is correct. Munson, where would you put the big wheel to get the maximum positive shear a little to the right of point B? In other words, I mean using this influence line. It is not correct. Just to the right of B is not correct. Just to the right of B is correct. You see the difference there? One of them is, I don't know, let me guess. And one of them is, I've been listening to you even though he's been yakking in my ear. Yes, that's correct. Just to the right of B. All right, guy in the middle. Yeah, but I don't have a name on you for some reason. Wait, maybe I do. I don't know. I don't. I must have. Yeah. I was probably hoping that you... Well, never mind. Don't say that. Where would you put the little wheel? That is correct, with the big wheel going right there. But I'd want a little more specific number than to the left of point C. Well, no, that's you. Your truck. Your truck is only 10 feet long, so unless you got a truck stretcher. Very good. That's where you'd put it. You'd put it right there, and it would be 20 kips. Right in the middle. Dupkin, where would you put Dopkin, excuse me. Dopkin, where would you put the lane loading? Is a good start. No, that's true. If you go look at the initial writings of Einstein, he says, MC squared. Where would you put it?
Between A and B.
That would give you a positive. That's a good start. I'll let you go with that. Plumber, where else would you put lane loading? Yeah, it's correct, because you see you have a positive influence line in there too. And if you say, oh, well, you didn't color it in, so I really wasn't sure where it was in all those lines, I understand. Then if I ask you for the maximum negative shear, slightly to the right at B, Macy? Macy here today? No? Oh, okay, sorry. Where would you put the 40 kip load for the maximum negative moment, a shear, just slightly to the right at B? Right on D is the correct answer. And then the little wheel's going to go here. Is that right? Yes. See how you can talk them into just about anything? I think we should rob a bank. You go do it, and you bring me the money. Where do you guys suggest we put the little wheel? Off of the span, so it does not detract from your answer. That's good. All right, I think that's, there aren't many more than that. They just all have the same idea to them. I had all kinds of possibilities here. Now, these get a little ugly, but this is the way these things are really built. The cars travel in this direction. Thank you. I knew I'd forget to do that. The cars travel to the right and to the left, as do the big trucks. And the beam that you're studying does not have a load transferred directly to the beam. What happens is they put the load somewhere on these top surfaces, these top slabs, these top beams. Then these beams run across between beams that are running in the long direction or across the bridge, and then this load, this beam here, runs the length of the bridge. So what happens is, I want to know, let me see, I got the car shown wrong. I'm going to have to show it with the wheels on the side. The car, you can put the car anywhere you want to, and you can put the truck anywhere you want to, and you can put any number of them, and of course it depends on the dimensions, how many you're going to get on there. But basically, I still want an influence line for a unit load. And the unit load starts out on the left-hand end, and it runs across, and when it's halfway, the reaction on this girder is 0.5 and 0.5, and that 0.5 pushes on the beam, and it causes some reaction at the reaction. See how many of these I got. I only got one. Don't know why I didn't make more copies, but that's okay. So what I want is I want you to run your unit load across from side to side, and I want to show you how to get, for example, the bending moment at F. Now, I told you these influence lines always come out straight lines, and they do. But the problem is once you start putting things on top of it and sometimes supporting it off the span and sometimes not, then the basic influence line is still a straight line. But all of these things raise up at different heights. So you do get some rather strange looking results. So what I'm going to do first is I'm going to tell you is that there is a beam. It is supported here. I had to put a piece of graph paper under there so I could halfway line things up. And it has a support right here. And I do the same thing. I either raise this reaction up one, and wherever all these other little pieces go, that's where they go, and I don't care. Or I cause a unit kink at F to get a shear influence line. Or I put a bending moment at F. I kink it 45 degrees, and then I put it back up on the supports, and I let all these people go wherever they want to go. So I'm going to do the moment at F. And the reason is I pulled this out of a book, and he showed me the influence line, and I said, geez, man, that can't be right. But it is. Here's what we're going to do. We're going to put a 45-degree kink in the structure. We're going to notice that there's where the pinhole moved, and that's where it belongs. And this piece right here is still right here. And so what I'm going to do is I'm going to show you the deflected structure as received from your house. I don't want to draw a wiggly line because I want my final answer to be a wiggly line. Here's what the influence line looks like. It goes right to here. And then it kinks at a 1-to-1, 1-to-1. Like so. And then that's the end of it. That's the way it came from your house. You'll notice here's a pinhole, and here's a pinhole. And there really isn't any beam back there. Now that's the main thing that I've asked you for the influence line for. If I ask you for the influence line for CD, because I was designing that little piece of steel, it would have its own personal little influence line for shears and moments and reactions and anything else you wanted to know. But this particular company is planning on splicing this beam at this point, and they want to make sure that the design of the welds at that point are appropriate, and therefore they've asked me to generate the influence line for a moment at F. So the influence line for the moment at F. Now I was getting ready to take it back to them when I realized that's no good because it's not properly connected. The pinhole there doesn't agree with where the reaction is. And I counted how far it went down. 1, 2, 3, 4, 5, 6. You say, you didn't count how far it went down. Yes, I did. Since it's over 6, it's down. 1, 2, 3, 4, 5, 6. Well, yeah, it had to, because I couldn't get Word to make my little thing square there. I didn't know how to do that. So, yes, I cheated. So I'm going to roll this guy up 6, at which time once he gets up there, I can put that pin back in there and everything will be fine. So here it is, rolled up 6. That means that this point here also rolled up. As a matter of fact, since it was 1, 2, 3, 4, 5, 6, 7, since it was 8 meters away, and the guy who rolled up 6 was 8, 9, 10, 11, 12, 13, 14 away, this guy rolled up 8/14 as much as this guy rolled up. I mean, that's just the way sticks work. When you have a stick and it rolls about a point, this point here moves in proportion to how far out he is from this measured point. That is to that as that is to that. You say, well, that's not fair. Your stick is bent. Well, let me show you my bent stick. There's the bent stick right there. Well, you can't even see the bend in there. You say it was 45 degrees. You didn't draw it 45. Well, it's 45 degrees so that I can get the right numbers. It's not really 45 degrees. Nobody would do that to a beam. So I'm going to roll this up 6. So this point's going to roll up 1, 2, 3, 4, 5, 6, 7, 8. 1, 8, 9, 10, 11, 12, 13. 8 fourteenths as much. So the height of this guy right here is 8 fourteenths of 6. Oh, I thought I had a number wrong. I was saying, I can't be wrong yet. And that's equal to, so 8 fourteenths is 4 sevenths. 4 of 7, 6, 12, 24 sevenths. Nope, can't do it. Give me a calculator. Psst. Got a calculator? Oh, you can text all day long, but you can't calculate. May I suggest you trade that in?
I got 3.43.
That's 3.43, thank you. Off your phone? What'd you do? Text mom and have her respond off her 3.43. All right. 1, 2, 3.43. Thank you. So that's how far that point rolled up. This is the influence line if people would just leave the dang beam alone. But no, they had to put all those little pieces on the top of it. 3.43. Okay, so now I'm going to show you the little pieces up on top of it. And I'm going to show them one higher just so it got a little height there. It's not going to change anything. We're just going to basically change the 0 height. This little guy on this end is, well, let me think about this. He's right here. The truth is he's right here, but I'm moving him up 1 just so I can get him off of this so you can see it. Then the next one is 2 meters over, and that's 2 meters over, and I'm going to add 1 to it just so you can see it. That puts him here. Okay? I hope what you see is that above the true influence line for the beam we're working with, I went up 1 unit. But this one was on the ground, so it didn't roll around when the beam itself moved. So the influence line so far looks like that. Now then I'm going to go to the next girder. It's 6 meters out. There's 1, 2, 3, 4, 5, 6. And I'm going to put a point right here. The truth is, it goes right there. I'm just moving it 1 out of the way so you can see it. And the influence line between those 2 points now looks like this. And lo and behold, because this guy didn't roll up when the beam rolled up, this influence line for the beams really got a kink in it. Now I'm going to go to D. D is 2, 6, so 6, and 9 is 10 meters to the right. 1, 2, 3, 4, 5, 6, 7, 8, 9. We're talking about this guy right here. And I'm going to go 1 higher just to get it off of there so you can see it. Or either that or I can just tell you these are 1 tall. And of all the strange things, look what the influence line does. And then finally, this one right here is right on top of this. Let me move it off 1 just so we can see it. Here's your influence line. With a wiggly line. With this as 0. And again, it tells you where to put the wheels, where to put the uniform loads, the lane loadings. And you can tell the values from that. First, if this is 3.43, then at the 2 meter mark, this was 2 out of 3.43. I'm sorry, 2 out of 2, 4, 6, 8. It's 2/8 as big as this number right here. Somebody with a real calculator. Is it 2/8? No. It is 2/8 of this number. What is 2/8 of 3.43? 0.86. So this thing right here is 0.86. That would be, this is an influence line for moment, so the units are feet. And you see that's what he got. Then you can tell me how high this number right here is. You could just pick it off the thing, probably plenty close. That height to this dot right here, that's out here 1, 2, 3, 4, 5, that is 6/8 of this number. What is 6/8 of 3.43? 2.57, thank you. 2.57 feet. And here is his height. This number is 3.43 tall. And this number is 1, 2, 3, 4, 5, 6 meters wide. And you're out here 4 meters from this end. So what is 1, 2, 3? What is 4/6 of 3.43? $2.29, thank you. There's a guy who wants to go home sometime. 2.29 feet. And of course this number then here is 0, and this one down here is 0. And so I can tell you the areas under those influence lines. You want to know the area if you happen to put load over this area right here between those 2 points. The area under that influence line is this height plus this height cut in half, gives you the average height multiplied times the base, 1, 2, 3, 4 meters wide. That would be the area under the influence line. That is the number that you use when you put a uniform lane load on there. So it works for weird stuff like this too. I mean, the rule, the principle, is just developed from mathematics and doesn't have any choice but to be right. The only question is when they get really strange looking like this, then they're a little harder to do. And the book just gave up. I'm not sure why. I know he knows how to do this too. But he cut the beam and cut the beam and cut the beam. When you take a look in our text, you'll find that he used the method I told you. Just keep whacking around on it until you get all the answers you need to plot the diagram. That's where I was learning how to do it. All right. Here is the beam. The beam itself is supported on the ends. Get back to something a little more normal. And these are 6 feet apart. Well, let me see here. They're 5 feet apart because I got marks at the 5 feet mark. And this is point A, B, C, D, E, F. The beams go across the top, little beams. They then transmit the load down into the main beam. And I would like to know the shear just to the left of C down inside this main beam. Influence line for the shear at C minus. C minus means just a little to the left of the beam. So here's what I would do. I would take the beam home with me, and I would bend it in shear 1, and I would bring it back out on the job site, and I'd say, one of the pins lined up nicely, but the other one is off by the number 1. So I would roll the beam down on amount 1. This point right here then would roll down, would roll down, would roll down. And these little lines here would go with this, except, let me see how I'm going to prove this to you. As this beam as the unit load rolls across this piece right here, he's putting the load only on the ends. And so what happens is the beam itself wants to deform like that, but because this is only puts loads, it doesn't put loads in this region, this piece doesn't really apply. What happens is because of this little piece in the middle, looks like that. So in other words, shear somewhere in this panel. Let's see, I don't want to shear at C minus really. I'm trying to, I can give you shear at C minus, but I want from C to D. In other words, I want to know the shear anywhere in this region right here as you run this thing across this top. Now, proof. Let's do it by pieces because that's easy to get. In other words, I'll draw you the shear influence line as it would look if I cut it at C. I'll draw you a shear influence line like it would look if I cut it at D. The truth is, because you have this little guy across the top here, neither of these really applies. So let's put the unit load, let's just say, at B. How much reaction do I get on each end? Did I wake you? No. How much reaction do I get if I put a 1? How much reaction do I get on the ends? Come on, guys. Right? 1 times 5 divided by 25. Okay. If you cut the beam itself now, somewhere between C and D, you're going to have how much shear? It's going to be 0.2. You got 0.8 up and 1 down. Going to be 0.2. I'm sorry, 0.8. No, that's right, it's 0.2. See imbalance of these two? What's going to happen when you move the load over about here? What's going to happen when you move the load to the right? Let's go ahead and move it all the way to there. Oops, thank you. How much reaction am I going to get here now? 0.6. Something fishy here, isn't there? All right, with the load just to the left, I would have a shear of 0.6 minus 1, which is how much? 0.4. All right, now what's going to happen when you move the load just a little to the right? How's the reaction going to change? If I swamped your brain, how much is the reaction going to change if I move it just a little to the right? So it's not going to change at all, right? All right. And now then, let's see how much load this is going to cause on this. All right. If I put the 1 right here and move the load just a little to the right, normally all of a sudden the load disappeared from the free body, right? But the problem is now is you have put it on this little guy right here, and that load is still coming in. So it's still there. Let's say you move the load to the middle. Find the middle here. Let's say you put the load in the middle. I say, golly, if you're going to cut the thing in right in here somewhere, it looks like the load has left. But it hadn't, has it? Because it's still pushing down a half here and a half on this side. All right, let's do some more of this next time, because these are used all the time. Okay, hang on.